All right, good morning, everybody. Welcome to our weekly core protocol sync. Today, we're going to go into much more detail, giving updates and talking about some next steps we have planned for our core protocol, our consensus layer, our networking layer, our distributed storage network, and some of the R&D aspects we've been doing. So to kick it off, let me just give a quick update on where we are at with consensus V1 and V2 and Dsm V1 and V2. So we currently have, for Gemini 2 incentivized testnet, or the testnet which we're launching, we have a version of consensus, which is basically what's in our white paper, a refined version of what's in our white paper. And we have been working on a new version of consensus, which we're going to be publishing some documentation about in the next few weeks. But we have been working on a new version of consensus, which is basically just much better overall, more secure, more environmentally friendly, more energy efficient, simpler from an implementation point of view, and easier on, I guess you could say, the users on their hardware. And so along with that, there have been some changes to the distributed storage network, sort of the decentralized storage aspect of Subspace, which we've also been working on, first properly documenting the V1 implementation that we have, because we never had any documentation for that. And then adjusting the Dsm design to reflect some of the changes in V2 consensus, because it has implications for the distributed storage network as well. And yeah, so that's kind of an overview of what we've been working on. Nizar's been working on the consensus layer, Shanil's been working on the distributed storage layer, and Daria has been working on a lot of the formalization and the research, and I've been working on trying to keep it all tied together with everybody else. So I guess given that, Nizar, if you want to dive in and give us an update on consensus, what you've been working on.
Okay, you should be able to see this. So last week there was this small update to the tests in the plotter. The challenge here was that it was working accidentally, basically. We had this kind of test input that has 6 entries. However, when we are running actual tests, we were only starting it from the second element instead of from the third, even though the comment was supposed to mean that we are starting from the beginning, from the middle. And because of that, everything was kind of shifted nicely in the way that it actually worked, like tests were passing. However, in the version 2 of consensus, I'm changing the hash function, and that implied that the whole, like everything basically moves around because the hashing is different. And I discovered it actually no longer passes. So this was a small change to make it more readable, and also to fix those offsets such that tests actually pass after that. And yeah, this was just an interesting discovery that we had tests, they were passing, but they were not 100% correct. So that's a small thing. The other thing is on the implementation of the consensus. I have a branch, it's still work in progress, it will still change, but I can kind of give you an idea of what it looks like. So we are using libraries from Dusk project, from Dusk network. They have this Splunk library, and they have their own implementation of BLS 12 381. And we are using that to implement some of the KZG stuff. They have those modules internally. I had to make a fork in our organization to expose some of those internal data structures so we can use them. Polygon Novel actually uses the same approach. They forked it and exposed some of the data structures with the same primitives. In the end, we had to re-expose those data structures in a way that makes sense for us, because the terminology didn't really match the terminology in the papers. So in the end, we have commitment, which allows us to commit to the whole polynomial with a whole bunch of values. And then we have a witness for a particular value in the polynomial evaluation. And we have this like wrapper data structure, which has public parameters that will be the result of the multi-party computation ceremony. There is a way to generate just random public parameters for testing purposes, but you can also provide them explicitly if you have one. In terms of what you can do with this thing, you can provide a slice of memory. It should be actually a multiple of 32 bytes, but only 31 byte, or more specifically to 54 bits are usable. And then it will give you a polynomial back. Then using that polynomial, you can commit to it, and you can get a commitment. And then with polynomial, and knowing how many values you commit to, and the index of the value that you provided in the polynomial creation, you can actually get a witness for that particular value. And then later, if you want to verify it, you need to have commitment. You have to know how many values there were, the index of the value you want to verify, the value itself, and the witness. And then it will give you true or false whether it was committed to and witness was correct or not. This is kind of high level, easy API to use. There's quite a bit of math I don't fully understand under the covers, but it is based on the libraries that we are using. There are links to some of the examples at the top where this code originates, and it seems to work. There is a small test case. We basically generate some data, and we erase last byte to make sure we don't overdo in terms of the amount of data we store in it. And then we create an instance, we create a polynomial, we commit to it, then we chunk values, and we count how many we have. And then for every value, we try to create a witness and verify it. And all of that goes through correctly. In terms of where we actually store the values, we are storing them in the values of the polynomial, not the coefficients, such that we can commit to the values themselves. This is something that was important. This is not the first version I did, but Daria pointed out that that's how we need to do it. I guess any questions about this so far? Okay. So the next commit after that was no, this is a simple commit. Just changing the feature check, doesn't matter. Here, I've created more wrapper types. I wrapped polynomial, so we don't expose the original one. That way, we can have better API tailored to our use cases. And I also added some additional methods and derives for the commitment and for witness. So we can convert it, or export it to bytes. We can construct it from bytes. We can convert it between these slices of 48 bytes. This is the fixed size one that we care about. And then there is also implementation for encoding and decoding using scale codec. There is typo info in case we want to use it in the runtime somewhere. Same for witness. And we have a whole module for the Saturday serialization, deserialization for those data structures. So basically, we can use this everywhere we need, as we did with the regular hashes, which were 32 bytes. But in this case, we have nicer data structures. And after that, I had to refactor the archiving-related data structures and APIs to use U32 instead of usize in many places. Usize is a flexible size, and I wanted to make it explicit that we do not expect to have, let's say, number of elements in one segment in terms of pieces that is bigger than U32. So better be explicit about that, and that requires changing a whole bunch of stuff, but it's just data type change, and we don't really support U16. That's also one of the reasons. It would have compiled, but it wouldn't work. In this case, it would just crash sooner. And after that, this doesn't actually compile fully, but the idea here is to refactor archiver and replace the Merkle tree we had with this fixed size commitment scheme. And that will allow us to change the witness size according to specification, resize all the data structures, and we should be 20-30% the way towards the version 2. So this is something I'm still working on and will continue working on. And yeah, after that, we'll go to other unimplemented parts of the specification. I think that's most of my progress this week.
Okay, Nazar, thanks for the update on that. So we have BLS signatures and KZG commitments. Are we still using the, sorry, go ahead.
I don't think we are using BLS signatures.
Oh,
BLSR for KZG.
Yeah.
Okay.
It's like internal primitive there.
Okay, got it. But the erasure coding scheme is still Reed Solomon, right?
Yeah, I'm not changing it yet.
Okay. Yeah, I don't think that's by any means a critical feature for V2 of consensus. That has much more to do with distributed archiving, which is a later goal. So we don't need to worry about making sure that they match the KZG and the erasure coding scheme match up right now.
Yeah, there are many places in our new specification where we are relying on this fixed size commitment scheme. And I thought that was the perfect example to tackle first. So we have the API figured out, and we can use it everywhere we need, and we can readjust all the data structures to be fixed size. And from there, it will be easier to work on the other stuff.
Right. Okay. And after you have the archiving implemented, what do you see as the next steps after that?
Oh, I need to open the specification. So encoding function will probably leave as is for now. I think we can move to the proof of space construction. I think it will involve wrapping the chia stuff.
Okay. Daria, could you speak a little bit about the comment Nazar made about the, I guess there was a version 1 of the implementation versus version 2, but you pointed out that something needed to change. Maybe you can cover that, Nazar. I didn't quite fully understand that.
Yeah, I think what Daria wrote initially there was mostly how it is explained in the paper. And Plonk library actually uses slightly different terminology. For instance, when we commit to the whole data set, we create a commitment. But then when we commit to a particular element, they also call it commitment, but we are calling it a witness for that particular value, for instance. And for the root, they don't have any special name at all. So I was just trying to change the API a little bit to have naming more in line with the paper and with the use case that we have. And also some of the arguments. For instance, there was no argument for number of elements we are committing to, but apparently that's an important parameter in case we are committing to actual values and not to coefficients. So I had to introduce that. And we were basically discussing with Daria asynchronous over the weekend what that should look like. And I think this is the first simplest API. We'll probably extend it with batch commitments and stuff. But for now, this is, I think, sufficient to cover some of the simpler cases. It's nothing major. Just like there was expectation, there was a reality of how library works, and we have something in the middle that is tailored to our use case.
Yeah,
Okay.
we basically had to figure out the matching, because I made the spec based on the KZG original paper, and then there are a lot of libraries that all use slightly different naming, and then well, I have settled and recommended to Nazar the Splunk library from Dusk, but then we had to rename things basically to understand what they mean by the names versus what it is mathematically. And I guess we figured that out because there's always confusion between witness and proof. So they call proof a data structure that contains both index value and what we call witness, which is what they call a commitment. So it was a little bit confusing, but I think we figured that out. And yes, as Nazar said, it would also need batch proofs, well, batch witnesses. And and then we also will need to have to figure out the way to set up values and figure out the exact number of public parameters that we need to have based on the sizes of the data that we want to commit to. So this is some of the open things.
Yeah, and the proof data structure, we are not using that at all.
Mm-hmm.
It just wasn't necessary for our use case. That's very specific to what they're doing. I was trying to find some of the public parameters for this that are from some kind of ceremony that happened prior. In Polygon and Whale, they just take Cha-Cha random generator based on seed, and they just provide 42 as a seed. That's it. That's the whole set of random parameters. So I guess they don't have it on the testnet yet. And I wasn't able to find anything from Dust Network either. So just generated a random number from 64-bit range and just put it as test public parameters for now.
Okay. Not a big deal at this stage.
I mean, if we would like
use-
to test bigger numbers, we would save these parameters, not regenerate them every time you try to test, because the bigger it gets, the longer it's going to take. So.
Okay. So I was doing some research on this, and I think there's this notion of subvector commitments, which was done after the original KZG paper, and almost all the implementations that actually use KZG now are not based on the original paper, but they're based on this extended notion of subvector polynomial commitments. And I believe Plonk uses that. I know Halo uses that for sure. So perhaps these elements are actually subvector commitments, and that's why they're called commitments, because technically that is a commitment as well. Because in most cases, you actually you don't want to commit to a data point, but you want to commit to a group, like a subvector. Is that possible?
So there are two different things. So there's a subvector commitments, which means that you commit to multiple points within the same polynomial. And then there is aggregated commitments, which means that you commit to points across different polynomials.
Right.
And which one we're going to use is going to depend how we position our data, like flat or kind of stacked records that we commit across them. So we still have to decide that. So the way we're going to implement batch proof is going to be either the subvector or the aggregated. So we will have to decide on that as well. The way that they called it in the Plonk library, they call witness not the actual final proof, but like a quotient polynomial in the median evaluated in that secret public point. So they called it a commitment to witness. So it was just confusion in terminology. But in Plonk, you can do the aggregated commitment across different polynomials. But I didn't see whether you can do a subvector commitment on the same polynomial, but I guess with a small change, we should be able to do that as well.
Yeah, because those are kind of two solutions to the same problem, right? You can either generate all the individual data witnesses together and aggregate them, which is like sort of the naive way to do it, or you can use the subvector commitment, which is supposed to have a better computational efficiency, is my understanding. It's like an improved way to generate that batch witness, as long as the items are contiguous.
No, I think it's like orthogonal. So subvector commitment is when you have one polynomial for all the data and you just take the points. An aggregated commitment, and when you have different polynomials and you kind of take like a column or different points scattered on them. So it's slightly different.
Maybe we'll take this offline. I think we're confused about something here. Okay. Okay. All right. That was all the questions I had about your stuff, Nazar. Anything else we need to cover there?
No, I think as long as we have reasonable API, we can change implementation later. Just was difficult to figure out this initial API, understand everything.
Okay. All right, Shamil, we'll turn it over to you if you want to give us an overview of the DSM and what you've been working on.
Sure. Currently, I work on the Dsm V2 design. I brainstormed with Nazar and Jeremiah most of the required features from available options, and I narrowed down options to the best single variant form on such questions like high-level DSM API, high-level DSM architecture, different workflows like how to put an object into the DSM, how to receive pieces reconstructions, etc. We have several open questions like how to handle object mappings, but I think we're close to the finishing of this design process, and I hope that this week I will start implementing the first versions.
Okay, Shamil, would you mind maybe sharing your screen and just going into a little bit more detail on the V2 current version of the V2 spec and just reviewing these open questions, even if we don't have time to address them right now.
Okay, sure. Do you see it?
Yes.
Yes.
Okay, so currently we have 3 open questions which will affect the overall design. They are how execution domain influence block archiving and object mappings, what are object mappings, archival storage, how we will do that, and what peer types will store the L2, which is a cache for pieces and object mappings in the DSN. So will it be only farmers or other peer types like nodes? So these open questions are just main for this design iteration. Did I answer your question?
Yeah, I guess we covered the open questions, but maybe it would be helpful for Daria and for the community if we just went through a high-level overview of the Dsm V2 design and kind of how it differs from V1.
Okay. For the second version of the DSN, we introduced 3 levels, as we call this, layers, for them for the network, which are L3, which is layer 3 object cache, layer 2 or pieces and mappings cache layer, and L1 as archival storage. So these 3 layers will handle all these interactions between different requests in the system. So upper 2 layers, layer 2 for pieces and mappings, and layer 3 of object cache serve basically to increase the speed of getting the information from our archival storage layer, because we see archival storage layer as a cold storage, and it will take some time to retrieve information from there. So we introduced several additional layers to handle this. This will add more complexity to the system, but it is a good trade-off, I think. Also, we simplified a lot networking layer because we removed relay nodes from the system. We introduced them to handle single port mapping to farmers, because previously we had additional nodes, which will have a virtual node for each plot that farmer have, and it could be just multiple virtual nodes per farmer, in extreme cases up to several hundreds virtual nodes per farmer. And we remove this complexity, and with that we removed also these peers or peer types from our network, relay nodes, and these virtual nodes in memory for farmers. I think this is the main benefit from the new design, because we are simplified a lot. I think we will introduce some additional ways, like additional features of the system, like object reconstruction, because we need somehow to get objects from the network when it is missing in our caching layer, in layer 3. I think that's it.
Awesome. Thanks for going through that, Shamil. And thanks for all the hard work on that. I know you've been doing a lot of research and design and writing over the last few weeks to get this ready. Looking forward to moving into implementation soon as well. Daria, do you have any updates about the V1 spec formalization? Have you been able to review that or sync up with Shamil on that yet?
So I've started on converting Shamil's document to DSN, but I'm not sure how to structure it really correctly, and there are some pieces that I don't think I quite understand enough to write them down. So I was kind of indecisive. So I also was doing a lot of KZG stuff, so I didn't really pay attention to that. But I have set up a call with Shamil tomorrow, so he's probably going to be able to. He's surely going to be able to clarify that for me, and also help settle on the format of the spec that it's useful across V1 and V2, so you don't have to change that. So that was also one of the things that I didn't want to dive head first without knowing the V2 structure.
Okay, that makes a lot of sense. Yeah, and I just wanted you to have a chance to look at it and start asking the questions you were going to ask, and not have to wait until V2 was ready. So that's why, you know, even though we're going to deprecate this V1 spec, it's still important to. There's going to be a lot of commonality between them, so it's good that you're focusing on the common parts.
That's what I. Yeah, that's what I understood it should be done. So it should be a V1 spec that's like should be transferable into a V2 spec.
Yeah.
Yeah.
Okay. Okay.
So for this week, as for my.
Sorry, Darius just had a couple more things for Shamil before we move into the trigger section. Okay, Shamil. So we have these open questions we need to resolve. You're going to need to sync up with Daria to answer her questions so that she can work on formalizing this. I think the next steps are going to be, once we resolve this, is to work out a basic implementation plan and a very basic high level like roadmap milestone plan for this. So as soon as we have that put together, I think we can get started on an implementation, hopefully by the end of this week.
Sure, I have in mind just a brief sketch how to implement this first version. I will just write it down on some page.
Great. Okay. Any other questions from anyone about what Shamil's working on, or comments? Okay. All right, Daria, if you want to go next.
Yeah, so as I've already said, I've spent a lot of time on various papers on KZG and erasure coding to make sure that we settle on a scheme that is kind of like future-proof, as we want to transition to scalability and proving the correctness of erasure coding. And I think I've understood a lot of stuff. I have also added one more tentative scheme that we could employ, which is kind of similar to what Polygon uses, but not quite, because they don't have like a notion of pieces and things. Then there were like at least 3 different layouts that I've thought on that we need to discuss at some point. Then there is the Dsm stuff that I'm going to be mostly working on tomorrow. And as for the spec V2, the proof of space stuff has been written a while ago, and it has been sitting there unchanged. Since for the last weeks, we have mostly spent our time on the commitment and erasure coding. But I don't think, I'm not sure you have gotten a chance to go through that, like actually read it through. So that would be very useful, because it's been sitting there for a couple of weeks now.
Yeah, I did get a chance to review it at a high level, and it made sense, but I haven't gone into it in the level of detail that we did last time. So yeah, I'll make sure to do that before our call on Wednesday and give you any feedback on that.
Yeah, and also before Nazar goes into implementing that, because he's moving really fast. It looks like.
Yeah, for sure. Yeah. Okay. Can you give us a little bit more detail on the learning about the polynomial commitment scheme and the erasure coding and how they fit together, and how you're thinking about that right now?
So there was one ambiguity that I have clarified. That is, so there's like flat scheme which is basically what we are using. We have all data in the row, and we want to make a big polynomial over it. And then we want to commit to all of that. Though we said there is some issue that with the data size of a segment that we want to have, that polynomial is going to be way too big to be confidentially feasible. So we want to probably run a test on like big amount of data and see how long that actually takes. So that's one thing. Then there is a second type, which is what Polygon does, similar, and it's also what is described in the efficient second proof of erasure coding paper, which they call a 2D scheme, which is not the same 2D as Ethereum 2D, which basically they structure data.
What's the what paper are you talking about?
Second erasure coding proof system.
Oh, okay. The one that's part of the Avid literature.
Yeah.
Okay.
That one. And so that scheme is basically they stack messages in a matrix, not like flat, like in a matrix. And they erasure code in one direction, but commit in rows. So basically, they erasure code columns, but commit to rows. And that would be the way, the use case where you would have in aggregate commitments over many polynomials, for instance. And then there is Ethereum scheme, which has a 2D erasure coding, where they erasure code in both directions. So I think now that the kind of erasure code in one direction but committing in the other direction should be the way to go, because it also matches the erasure coding proof, and it seems simple and elegant enough to me. Though there is a way to figure out how do we want to fit pieces in there, because like Polygon and those papers, they have this matrix is more or less square. We're going to have it way bigger in one direction, because we have less pieces that are like many more chunks, and we need to decide whether we want to, commit to rows and extend shorter, or well, which direction we want to do what. And that may include basically trying to write them as code and see which one's actually faster.
Okay. Okay, that makes sense. And I think that the scheme that Polygon is using, from what you're describing, is actually similar to the Avid PR, Avid with provable retrievability scheme that is in that paper for whatever it is, data availability for rollups that Joachim wrote. Sounds very similar because it was based on homomorphic fingerprinting and erasure coding, like that other paper. So in my head, I thought that Polygon Avail was using the same scheme as Ethereum too, but I guess that's not right. They're different. There's really two questions here. There's one about what are we going to use for Gemini 3 and for V2 consensus, which is almost certainly going to be a flat scheme. If there's a question about how much is computationally feasible to encode in a single pass, then we'll just have to make the chunk size smaller to reflect that for now. Then there's another question of how do we do like distributed archiving and all this stuff, which is probably going to, like the leaning has been, it's going to be more towards that scheme you just described, which Polygon Avail is using, which is like encode in one direction or commit in one direction, erasure code in the other direction. Then you can use this like magical property of the way things work to prove things, the way the math works. So I think I don't want that to block, I guess, any of the implementation work that Nazar is doing right now. But it's a really good research open question that we're going to resolve. But I just want to make sure that we're clear on those two different components.
Yeah, true. So distributed archiving is like way out of the map right now, but I think that this sort of polygon-like scheme of stacking things and then committing in one direction can actually be much easier computationally than just having a flat out enormous polynomial. That's what why I am looking at this right now, because it does look better than the flat scheme. It might be actually easier to handle and commit to, even
I
like
guess I can
for now.
clarify about implementation a little bit. The way I'm committing right now, I'm actually committing to hashes, not the data itself. It seems more complex if you commit to the whole piece, like in 32 byte chunks. And especially the fact that we have to have like 31, and then we have to have some padding. Like, I just wanted to make changes as minimal as possible for now. So instead, I'm doing very similar to what we did with Merkle tree, just like replace the commitment itself, but the mechanism is still the same. So something to keep in mind as we are concerned, like if you have concerns about the performance, depending on how far we are going into modifying the actual archiving process, it may not be a problem yet.
Well, maybe not yet if you're committing to hashes, but that should not be the case, in the final.
Sure. Yeah, we're gonna have to maintain some flexibility here between the implementation and the spec as we go through trying to get a initial version. But I think it totally makes sense just to use it as a kind of like a better Merkle tree versus trying to use it to like get all these nice homomorphic properties at this stage. So I guess that I'm just trying to separate that out just to make sure that it's not urgent to solve this like for the next phase, but it is probably definitely urgent for the long-term architecture to specify that, and like you said, to future-proof things as we upgrade.
Mm-hmm.
Okay, well that sounds promising. I think that's something we'll definitely need to cover more at the research sync. If you could, yeah, that's something I'd like to focus on and try to really clearly understand the differences between these three schemes. And I'll share a couple of papers with you about some of that stuff. You already have read the one on data availability for rollups, right? You're familiar with that scheme?
No, not that exact paper, but I will look at that one.
Okay,
But
I'll shoot you a link.
Okay. I think it is in your DAS document. I just didn't look at that one.
That's right. Okay. Okay. All right. Anything else on your side, Daria?
Yes. Then we also need to focus on finalizing the proof of space thing, actual steps. But yeah, I mean that should be almost done unless you have other comments when you read through it.
Yeah.
I would appreciate if you did.
Okay.
Because that is more urgent than the figuring out future-proof KZG.
Yeah. Yeah, I think Nazar and I are going to talk about it later in the one-on-one, but what I'd like to do is try to avoid using Chia at all in the first implementation and just use like an XOR function, like an abstract encoder. And then maybe do that on the next pass. But we need to have a discussion about the complexity of that first. So it might not be as urgent,
Okay.
like for tomorrow, so to speak, maybe for next week or the week after. Okay.
Okay.
But I know it needs to be reviewed so that we can move on.
Mm-hmm.
All right. Any questions for Daria? Final comments? All right. Great. Well, thanks everybody for the updates. Thanks for watching, and we will be working hard on getting out the the first iteration of version 2 of consensus in the DSN in the next few weeks as we prepare to launch that for Gemini 3, the next iteration of our testnet, which is coming out in the next few months. and also publishing more of these specifications once we have them finalized. And we're probably going to be sharing some more details on the background for why we're changing consensus as well. All right. Thanks everybody for watching, and we will see you again next week.